Good morning, good afternoon, good evening, wherever you are in the world. Welcome to Wednesday EMinar Day. And today it gives me great pleasure to introduce Hannah Petersen, who's going to talk to us about combining an experiment, a novel experiment she performed, combining land and lake bottom NT data. But before I do that, I'll just remind you all that I think we can probably stop telling you all this now, but go to the EMinar page to see previous EMinars and to register for upcoming ones, and that you're on a webinar, so you can change your audio settings, you can send a message in chat, you can send a Q&A, which Hannah will answer towards the end, at the end of the talk, and you can raise your hand if you want to speak, if we want to have some dialogue. We can bring people in to have a discussion at the end. Okay, so today is Hannah Petersen again, and I'm particularly glad that Hannah's offered to give a talk, because we'd like to hear a lot more presentations from younger scientists in this EMinar series. And Hannah's going to talk to us about combining land and lake bottom magnetotelluric data to study the volcanic systems in the Mono Basin. So Hannah earned a bachelor's in geophysical engineering from Mines in 2017, and then a master's at San Diego, working under Steve Constable in the marine electromagnetics labs. And Hannah's also worked in near surface geophysics as a field geophysicist, doing field work in southwestern US. And she's currently employed by Connor Consulting in Lakewood, Colorado, as a project geophysicist. So I'll hand over now to Hannah, if you want to share your screen.
Yep. One second, let me get my presenter view back up. All right, Alan, is that just the PowerPoint again?
Yep, it's
okay.
Looking great, Hannah.
Great, thanks. All right, yeah, guess I'll get started here. Thanks for the introduction, and thanks for having me speak today. I'm gonna present on some work that I did for my master's thesis, working under Steve Constable at Scripps. I graduated in June of 2020, so the work's been completed for a bit, but we are still trying to push out a paper or two on the work. So yeah, I'm excited to talk about it. I think possibly a couple of you on the chat or on the call have heard my thesis defense, so it's going to be a little similar to that, but threw in a couple new things. So as I said, the work was done with at the Marine EM lab at Scripps, and then we had collaborators from the USGS as well. So the area of study here is in California. It's on just the east side of the Sierra Nevada mountain range, which is kind of this darker area here. And if we zoom in, you can see a couple, popular tourist destinations around Mammoth Lakes. Yosemite National Park is to the west here, and Mono Lake sits here, just right off Highway 395. So just a little background on the geology of the area. So the whole area is called the Owens Valley region, which consists of the Owens River Gorge, Mono Basin, and the Long Valley Caldera. You can see in that photo there, the Sierra Nevada kind of sit above the caldera in the Mono Basin, Mono Craters area. So this is located in the Basin and Range province, which is sits in California and Nevada. And the whole area is a result of extensional tectonics. So that's going to be stretching and thinning of the crust, allowing mantle to rise and causing kind of uplift and downdrop of blocks bounded by normal faults. So the land's going to rise and break along fault lines, and then this is going to allow hot mantle to rise and migrates upwards. So this will be a big contribution to the volcanism in the area that I'll touch on. So to start with some of the features around the area, the Long Valley Caldera is the kind of the oldest of the volcanic features in the Owens River Valley area. So the Bishop Tuff was an eruption, 600 cubic kilometers spread over a couple thousand kilometer area. It actually made it all the way to Nebraska, they think, or present day Nebraska. So pretty big eruption at that point. You can see traces of the Bishop Tuff kind of everywhere around California and to the east. And the volcanism here is fed through a northwest striking dike, which again was allowed by that basin and range tectonic activity. And a resurgent dome has occurred in the last 100,000 years in the Long Valley area. So that's a relatively recent geologic activity. And then Mono Basin, more of the specific study area for this talk. So the Long Valley Caldera sits here, and then Mono Basin is kind of northward from there. So the basin is bound on the west by the Sierra Nevada fault. So you can see in this little figure here, we have the Central Valley, California, the Sierra Nevada mountain range, and then once you get over on the east side of that, you have this Sierra Nevada fault here and Mono Basin down below. So the basin was formed by uplift of the Sierra Nevada and White Mountain escarpments, creating the downdrop block. And then since then, the Inyo-Mono Crater chain has formed, which has consisted of about 30 pretty significant explosive eruptions, which began about 50,000 years ago. So relatively young. It's going to be some of the youngest rhyolitic volcanoes in the Western US, and is ranked as a high volcanic threat still to this day in the United States. Then going a little deeper into this crater chain. So it began south of Mammoth Mountain here. So this is just a little diagram. All the red are going to be the craters. And then if you go over towards the right of the figure there, you can see how long before present it erupted and what kind of eruption it was. So it started with these red cones down here. And then there's been since a pretty stark northward progression here of these craters. And so the most recent was the Paoha Island eruption, which happened only about 350 years ago. And so this figure here is the Panam crater, which is part of the Mono craters to the north right here. So Mono Lake, if anyone has been there, it's pretty interesting looking body of water. You have these tufa towers here kind of sporadically coming out of the lake. So it's going to be freshwater springs mixing with the saline lake water, creating calcium carbonate limestone. So it kind of creates just these big towers that come out at random spots in the lake and attracts a lot of tourists for that reason. It's a fairly large lake and it's saline. It's going to be more saline than seawater actually, and has a maximum depth of 48 meters. And So like I said before, the Paoha Island is the youngest of kind of these volcanic features that have formed just about 350 years ago. And so the island is formed of lake bed sediments and volcanic material from that eruption. So why are we studying this area? So there's been heightened geologic unrest here in modern history. So a couple of examples are deformation, such as the resurgent dome forming in Long Valley Caldera. Another important events that have happened are these CO2 seeps coming up through local faults. So this is a little schematic of that. And so high concentrations of this are going to pose a threat to humans living in the area, coming up through basements and in these snowbanks. And it can seep up through tree wells and into structures, into buildings. So they've actually put some of these warning signs at Mammoth Mountain ski area because they don't want people getting caught in these tree wells where that CO2 is coming up. I think it was about 30 years ago, there was actually a couple ski patrollers that did die from these CO2 emissions. So it's a pretty important issue to look at just for the health and safety of the residents and the tourists in the area. There's also been increased seismicity. So this is suggesting that there's changing pressure and movement of fluids and magma contributing to these earthquakes. So basically all of these together have just sparked concern for increasing threat of volcanic activity. And then this is just another example of kind of what's been happening in the area. The CO2 can kill trees in large areas. So this on the left here is an aerial image of some of that tree die off, and then these yellow areas are areas of tree kill that have been mapped around Mammoth Mountain. All right, so for this study, so I had a couple different objectives, kind of a couple on the interpretation analysis side, and then some on the more of the technical aspects and methodology here. So first objective was to process land and lake bed MT data using multi-station processing codes, and then the combination of these two data types for a 2D inversion. And then the third objective, to interpret the conductivity models to further study the volcanic systems in Mono Basin, and that's for the purpose of trying to forecast when the next eruption might be and kind of characterize what the systems are doing under the basin today. And then the fourth objective I'll get into a little bit later in the talk. It was to develop a process for upward continuation of lake bed MT data to use in the MODIM 3D code. All right, so why are we using MT to study this specific problem? It's probably one of the best tools to image geothermal systems, because in this case, the targets are fluids and heat sources, which are going to be electrically conductive in nature. And then it's going to contrast between more resistive host rock. And so overall, the natural currents are going to span a lot of different frequencies, so you can image structure at a wide range of depths, and we can get down to those deeper depths of penetration, multiple kilometers, like we're looking at seeing. And I'll note that since there is some non-uniqueness in MT data, just meaning that many different things can fall in the same range of conductivity, we're going to incorporate more geophysical and geologic information to validate the models. So a previous study of this area was done by Peacock et al. From the USGS. So they did some 3D inversions on land MT data that had existed south of Mono Lake. So you can see the lake here, and then the data set kind of stops right to the south of the lake here. And so they were able to show a super complex structure under the Mono craters, big vertical conductors at about 10 kilometers, and then the connection of these deeper conductors to shallower crust. So we have R1 here. This is their interpretation of their 3D models. R1 is a cold pluton that is actually outcropping at the Aeolian buttes. And then these C1, 2, 3 are crystal melt columns that they think fed the Mono crater eruptions through east dipping dikes. And so this was an interesting geologic result, and really kind of sparked interest in this area and doing more of a full interpretation of the rest of the basin. And so after this, they got, when interest was kind of heightened about this area, they decided to do the Mono Lake data collection. And so the USGS teamed up with Scripps, because Scripps was able to provide the seafloor EM receiver and kind of modify them to use in the lake, since they didn't have data anywhere north of in Mono Lake or north of there prior to this. So there were 21 stations in the lake. They logged 2 days each. And you can see here, this is the lake with the bathymetry mapped on it, and all of the stations. And then there was a remote magnetic station that recorded a couple of kilometers south of the lake. So this over here is Jared from the USGS deploying one of the receivers. They use this little boat on the lake to go around and drop all of their receivers. This is the schematic of the Scripps seafloor EM receiver. They modified it a little bit, shortened the dipoles than what was usually used on the seafloor, and made a couple other modifications for shallow water. And then following that in 2018, they recorded 24 land stations using Zong equipment. This again is Jared recording, and this is just a picture of one of the stations here with the vertical magnetometer. So these are 24 stations recorded overnight. So these are going to be the light blue, the MB stations in this map, and then all of the lake bottom data is in the little anchors. So one of the challenges for the project was that the land and lake land data didn't comply with the processing codes we were using that are usually used for the marine data. So they had to be rewritten into a format which was compatible with the multi-station code, which was kind of one of the tasks that I took on. And then the remote data were in the Scripps format, so kind of had to match the sampling frequencies from the land data to the remote data to use in the multi-station code. And so this here is just a figure showing in blue is the remote magnetic station, and then in orange is one of the land stations. So you can see that they're in pretty good agreement with just a small, maybe couple or millisecond shift, just due to the difference in the instruments. So that data was modified to be able to use in Gary Egbert's multi-station processing code. So this is a mathematically robust approach to improve remote referencing, and it can incorporate multiple stations in the same deployment. So I grouped stations together anywhere from 2 to 4 or 2 to 6 stations in the groups while I was processing, and that's going to improve the signal to noise ratio and diagnose possible bias due to coherent noise in the data. So kind of the method that I used was bringing in one noisy station with the cleaner data to improve the noisier station, and then processing the clean stations together. So This is just gonna improve the signal to noise ratio. And it's gonna create R transfer functions to use in inversion. So a quick comparison of processing methods. So the land data collected north of the lake was processed using the single station technique and multi-station codes as well. And so in the orange here, the remote reference was not used. And then in the blue is the processing from the multi-station technique. So they're fairly similar. There's a little bit of a higher bias in the orange data here, and then some discrepancies in the longer periods as well. And so the data was fairly clean as compared to other projects that they've used the multi-station code for, particularly in the seafloor, but it does kind of show that it was able to clean up the data a little bit. So I ran my 2D inversions in Mari 2D EM, which was developed by Kerry Key in 2016 when he was at Scripps. And this is a finite element code for 2D forward and inverse modeling. Starts with your EM data. You can put in topography and any a priori geologic structure. There's a model building assistant, which I'll show an example from that, and then you can run the forward and inverse modeling and view your result. And this is going to use the Occam inversion method developed by Constable et al. In 1987, which is an algorithm for generating smooth models from EM data. So I ran 2 lines for the 2D inversion. So I have these 135-degree lines here, A and B, so 2 different profiles, and each had 13 land sites in them. Line A had 9 lake bottom sites, and line B had 6 lake bottom sites. So I kind of took a line and then, kind of matched up these stations, kind of snapped them to this line, to these 2 lines to make the 2 profiles. The data was cleaned up using some existing MATLAB codes we had in the lab, and very noisy data were removed for inversion. So these were mostly the longer period data. And then this also shows where the remote magnetic reference was located in relation to the rest of the MT sites. And so this is a kind of a zoomed in image of the starting model that I used. The red portion is going to be the lake, and then you can see the little white triangles are the lake receivers, and then you have your land ones as well. So I used a 3-layer model for the lake as a fixed parameter because we're not measuring the conductivity of the lake. That's already known from the CDT soundings that were done at the same time of the survey. So I chose 3 separate layers here, one in the shallower portion, one in this middle portion, and then a longer layer at the bottom. And then otherwise I just used a 1 ohm-meter half space as a free parameter for the rest of the inversion. This is the result for profile A. So the line in red up here, the inversions ran on a 12-core desktop, took about 8 to 10 hours each, and did anywhere from 10 to 15 iterations. And I used a starting target misfit of 1. So in here you have your, so Mono Lake here is kind of this little more conductive area right here. And then you have, so the warmer colors are going to be conductive and the cooler colors are going to be resistive. And then just to zoom in on a shallower section of the result, I changed the color scale here to see the features a little bit easier, but the warm colors are still going to be conductive and cooler colors are resistive. So on here we have mapped faults, and the dips are just inferred by previous studies of the area. The faults are going to be these dashed black lines here, and so we have a couple smaller faults up here. Then the Long Valley fault is a pretty significant one as well. So we're seeing that the geologic features mapped at the surface line up pretty well with areas of higher conductivity. We have these volcanic vents and thermal springs up here. You can kind of see there's a pretty conductive areas under some of these vents. This area in red is circled as an area of interest. It's about 5 to 10 kilometers down, and we think is possibly a hydrothermal reservoir or magma that's feeding into a shallower conductive area under the lake. So kind of this highly conductive area feeding up through here into a more shallower conductive anomaly. And this makes sense because there's a lot of active hot springs under the lake. So kind of this conductive system here is attributing to those. And then the earthquakes are also plotted. I grabbed earthquakes from 5 kilometers on either side of the profile. And these are events from 1960 to present with higher magnitude than 1. And so we just thought it was interesting to plot these and kind of see the depths and the magnitudes of where these events were occurring. So the yellow one here is the highest magnitude, and it's kind of close in depth range to this magmatic body that we're seeing here. And then this is the second profile I ran, profile B. It's kind of showing similar behavior. I'll jump to the other plot here. So again, the warmer colors are conductive, the cooler colors are more resistive, and then I plotted the earthquakes on here as well. So we're kind of getting a similar result, which makes sense because the lines are parallel and they're fairly close to each other, just right across the lake from each other. So you're seeing the same conductive body here and kind of a more shallower conductive area right under the lake. These are the 2D data fits I threw up here. The data fits fairly well with some exception in the longer periods. And I'll note that the TE resistivities were removed for the land data due to sensitivity to 3D geologic structure. So that's why for some of these sites here, you don't have both modes. And so after this, I did some partial melt calculations. So starting with the hydrous andesitic melt conductivity model, which estimates the conductivity of melt as a function of water content, temperature, and pressure. So I found literature values for all of these variables and played around with them for a while. And so I did a partial melt estimation on that conductive area of interest that was circled in the first interpretation. So basically just approximating what fraction of the rock was melted. And then I used the Hessian and Strickman upper bound model which simulates interconnected melt. So once I had these conductivity values calculated from the andesitic melt model, I put them into the upper bound model to estimate the melt fraction. So what I got was anywhere from about 5 to 40% melt, and that's just depending on the water content and the actual temperature of that feature. So we have a little bit of a range there. All right, and then moving on to 3D inversion. So what the initial problem was that we, in MARI 2D, were able to put the receivers in that conductive lake water in the model like I showed, but MAUDIM can't, you can't include the bathymetry in that modeling. So what we had to do is use this data propagation to model what the response would be if the receiver is recorded on the top of the lake, so that we were able to put them on the surface in the starting models. So the diagram here shows just a schematic again of a layered lake with those conductivity values. So we have a conductivity and a thickness for each water layer. The receiver is going to be at the bottom layer. And so we use the 1D impedance recursion relation, which is calculating the impedance at the top of a layer as a function of the layer beneath it. So we're going to use this, we use this equation here to solve for Z at every layer. So basically we were taking the data points and solving for what they would be each layer moving upwards until we were at the top layer. And some forward modeling that I did for this in Mari 2D. So I used a 3-layered lake overlying a half space again. So the dashed lines are going to be if the receivers were just at the lake, sitting at the lake bottom. And then these solid lines are going to be if they were at the lake surface. So the difference in these results just confirm the need for modification for the data for inversion, since it does differ quite a bit, especially the higher frequencies. So in 1D, this was the approximation that resulted from the upward continuation of the data. The blue here is if the receivers were at the lake bottom, so the unmodified data, and then the orange is if they were upward continued to the surface. So you can see there's kind of the same difference in between the two, the modified and unmodified data, especially here at the higher frequency or the lower frequencies. And so I put the upward continue data into 2D inversion just as a validation to make sure that if we use the original 2D inversion with the lake in it, and then use the upward continue data, but put the receivers on the lake surface, that we would get the same result. And they did look pretty similar, which was a promising result for then putting into 3D inversion. So the 3D inversion was done using ModEM. Jared Peacock at the USGS ran those for me on one of their supercomputers over there. So we started with a 100 ohm half space with the lake as a fixed conductive feature. So here we have all of the stations used in the 3D inversion. The red are the lake stations, the blue are the land stations. And so we used that data from 2018 north of the lake, as well as the data south of the lake that had already been included in 3D models for their paper. And then the purple is just Paoha Island, and then the green is the Mono craters. And then this red line is just going to be one of the profiles, the 2D profiles that we grabbed from the 3D inversion. So this is the result, the preliminary result for the 3D inversion. So the resistivity iso volumes, these 3D volumes, are about 20 ohm meters, which is higher than we're seeing in the 2D result, but thinking it's just an artifact of the different codes. So we have Mono Lake here, and then kind of the same structure we saw in the 2D inversions of the feature kind of funneling up towards the nearer surface. This is a comparison of the 3D and 2D inversions. So kind of along the same profile that that red line showed on the map. And I tried to match up the color scales here. So warmer colors are conductive and the blue are resistive. And so they're agreeing fairly well. You're seeing the deeper conductor down here at a couple of kilometers, kind of 5 to 20 kilometers where we start losing some resolution. And it's using, it's kind of funneling up at one point to the near surface conductive area. And then these purple dots are the earthquakes plotted on the 3D inversion. So the agreement between the two models was promising, kind of showing the same behavior for the conductors. So when looking kind of more into the earthquake locations, the shallower conductors around here align pretty well with an earthquake cluster on the north side. It's kind of hard to see just by grabbing screenshots, but so it could be interpreted as hydrothermal fluids or partial melt or both. And overall, the models are suggesting volcanism is moving northwards still, and the next eruption likely will be north of Mono Lake, which is kind of to be expected from the recent geologic activity of the area. All right, so to wrap things up, so we've identified a shallow conductive feature under Mono Lake, which is connecting through a deeper, or through to a deeper conductor that's feeding the shallower portion of the subsurface, possibly through one of those faults or fractures. And we're thinking the shallower portion is likely attributed to hydrothermal fluids. It's suggesting northward progression of volcanism in the area, as I said, and the results are in good agreement with previous geologic, geochemical, and geophysical studies in the area. And more on the methodology side of things. So we proved there's a need to modify the lake bottom data for use in 3D inversion to mitigate that lake effect on the response, to be able to use in the ModEM 3D code, and the upward continuation using the 1D recursion relation proved to be successful in accounting for that modification. And the technique is useful for future shallow water MT work. As far as using it in marine settings, we aren't sure about that, but for future shallow water work in lakes and lacustrine environments, it's going to be useful. So what's next? More MT data north of the last data set would possibly show the extent of those conductive features near the Bodie Mountains, which sit just to the north of the area that was surveyed last, and more near surface work possibly in the upper 5 kilometers, maybe to map those hydrothermal systems a little bit better. The MT method is useful for mapping those deeper structures, but as far as getting better resolution in the upper or in the near surface, maybe using another method to do that. And then also time-dependent data could show at what rate these features are growing and moving, and this could help forecast the next big eruption if that were to occur. So I'd like to thank Alan for having me speak today. And also I'll acknowledge Steve, my advisor for this project, and then Gabby Lasky and Jeff Cook, who sat on my thesis committee, Peter Scher, who was a postdoc at Scripps while I was there, helped me out a lot with my project. Jared Peacock from the USGS as well for running the 3D inversions and helping out with the field work, and then Carrie Key for the 2D code. So thank you.
Thanks very much, Hannah. Absolutely wonderful. And wow, it's a beautiful part of the world.
Yeah.
I'll just jump in. We have one very nice question from Dennis, but I'll just jump in first. And that is,
okay.
What did you do to prove to yourself that a 2D model would be valid?
So you mean the 2D inversions?
Yeah. I mean, did you treat the data in any way to make it 2D like, or and how did you choose that profile, and how did you choose the strike direction? I just wondered, because it looks a very 3D area. I just wondered how you made the 2D decisions.
Yeah, so I actually ran a similar line that Steve had already run, just with the lake. So he ran it just with the lake data, and then I used kind of the same profile that he had already picked out, and added in the land stations to the north. The orientation of the line was along line of strike. And as far as validating the models afterwards, I just did my best with the kind of the geologic information that we had in the existing 3D models from the south side of the lake. So did that answer your question?
Yeah, no, I'm just really puzzled because often in a 3D model, you need more conductivity to get the same response than you would need in a 2D model. And yet you seem to have the opposite.
Yeah, sorry.
A lot more conductive material in the 2D model.
Yeah, it was more conductive in the 2D model, which I was surprised about as well. And the values, the conductivity values are actually higher in the 2D than the 3D. Yeah, I think it would be useful to kind of dig into that a little bit further and do more model validation and comparison of the 2D and 3D codes and results. So
yeah. So Dennis has a couple of questions, and then Max wants to jump in. And Dennis, I'm going to read the questions out so they get in the recording. Dennis asks, there appears to be less resistivity structure in your 3D inversion results than the previous USGS 3D inversion results from south of the lake. And his second question is, what other methods would you recommend to map the hydrothermal systems in the upper 5 kilometers in detail?
Thanks for your questions, Dennis. Yeah, I noticed as well in the 3D inversions, we had less resistivity structure, kind of that Pluton that was showing up in the previous result. I'm not actually sure what the cause of that would be. I'm guessing just the addition of the additional data kind of changed things around. The addition of the lake data in the 3D inversion would have affected the resistivity structure, especially since right under the lake appeared to be so conductive. So I'm not actually sure what the right answer to that would be, but I can. That would be a good thing I can speak with Jared Peacock with and see if he has any anything for that. And then as far as other methods for mapping the hydrothermal systems, so actually I have experience doing electrical resistivity in lake environments. And so I was thinking that would be a useful tool to kind of map the near surface in more detail and get down to couple meter resolution to be able to kind of better quantify the hydrothermal systems, and rather than just seeing a big conductive area, we might be able to see specifically where those that's popping up in the lake or outside of it. So that's the method I would recommend. Yeah, being in a lake environment is a little bit difficult, and your range of methods that you can use goes. You have a less of a range of methods that can be used in the water. So.
Okay, Max. Yeah.
I have a question about your upward continuation, which of course is sort of quite interesting, but I'm sure you know that this is also just an approximation, right? You're not fully accounting for the bathymetry, and you checked a bit,
right?
So if you want to, 2 questions. Have you checked when this sort of breaks down, or did you see any indications that at some sites it breaks down? And the second question, and that's probably more for the ModEM crew, which I think unfortunately I'm not in the audience. What particularly about ModEM precludes putting sites in the water? Because I think from a, if you want to, method point of view, I don't see any fundamental issue of doing that. So it must be something ModEM specific. Do you know anything about that?
So as far as the ModEM question, I think the issue is that you can't put the receivers. So if you have your model and then you have your layers of the lake, you can't put receivers not on the top of the model. So it would be, you know, as if the receivers were buried almost under the layers of the lake. So I think that was the issue there, was that we still wanted to include the lake layers in the inversion, but it would have technically had to put the receivers under layers of water in the model. So I think ModEM doesn't have that capability as of right now, but that also, yeah, that might be a question for them. And then for your other question for the 1D approximation, so yeah, I only did it for those handful of lake sites, and I definitely saw differences in where, so I'll go back to explain better. So for, geez, no, it's not letting me. Well, it's not letting me go back, but so yeah, I saw it like not work as well in more of the shallower or sorry, the deeper stations that had more water above them, which is why I at first did all of the stations under the 3 layers. However, some of the stations were under less water than the deeper ones. So I kind of had to switch things up for the shallower stations and include less layers above it. So I kind of saw it break down then, but yeah, I guess it would be interesting to be able to use it in another project and kind of see what the limitations of doing the approximation is for more or less water, less layers, and more data. So yeah, I'm not sure if that answers your question, but there definitely is more testing to be done with the upward continuation method.
Yeah, thanks. No, that's what I was looking for.
Yeah.
You know, one thing you could do, Hannah, is model the lake in 3D and look at the 3D responses and then compare that to your upward continued responses and just see how they differed. You know, just get the forward response of the lake itself with a uniform subsurface. And then you could even think to try to remove that effect from your responses. It's not totally correct, of course, because there'll be some mutual interaction between currents in the lake and currents in the conductors, but it might be a good first order way of removing the lake. But like Max, I'm a bit surprised at ModEM because you have to calculate the fields everywhere in the subsurface, everywhere in the Earth. So it really shouldn't matter where the sensors are.
Right. Yeah. Yeah, that would be. Yeah, I like that idea of, you know, validating with the 3D data. That's something good to know for any further work on this. And yeah, I think maybe talking to the guys at ModEM about what the limitations are would be useful. So
Dennis has a follow-up question. I suppose my first question will be better posed to the authors of the previous viewers yesterday, and perhaps there is scope for some joint work. I guess it's not really a question, just a comment. Thanks, Dennis.
Yeah. I'm still working with Jared there, who's the author on the previous paper, to do kind of some further 3D modeling, and I'm not sure what the plan is for more surveying or anything, but yeah, probably do a little bit more 3D modeling and validation if we want to push a paper out or anything. So
yeah, Dennis also follows up. We'd also recommend surveying a large-scale resistivity 3D survey. So DC resistivity. Of course, DC resistivity images the conductivity of Earth very differently, right? It sees resistors, whereas inductive methods see conductors. So they're very complementary methods.
Right. Yeah, it would be interesting to have both data types and be able to do some comparisons, and yeah.
Yeah, thanks, Dennis. I think there's no more questions, Hannah, and I'd really like to thank you again for offering to give your talk, and I think you're, perhaps a role model for other young people to step up. It's great to see people presenting their work and not being afraid. We don't bite too hard.
Not being afraid is maybe wrong, but no, yeah. Thank you for having me. I was really excited to be able to share this work and get some additional feedback on it. So thanks.
I'll close off now, and I'll just like to thank everybody for attending, and just remind you we'll have the EMinar next week is from Arseny Schleikoff on a package for processing data, a free package called EMP, and that's at 1300 UT 1st of December. And this recording will be up on MTNet as soon as it's available to me from Zoom, and then Hannah will send me the PDF. So thanks everybody, and see you all next week. And thanks again, Hannah. Bye.
Thanks.
Now.
Bye.